Dear all, welcome to all of you. I hope you're well and healthy in these turbulent times. I wish you all a warm welcome to this REvivED Water webinar presentation event. We as REdStack are honored that so many external guests will be able to follow the results of our EU REvivED project, and we're proud to disseminate them. And of course, a welcome to our project partners. My name is Rick Siebers, and as CEO, I'm responsible for the company REdStack. This webinar presentation is organized by REdStack as part of our participation in this European Union REvivED project. As you may know, we originally planned to have this live event with several presentations on the location of our pilot installation on the Afsluitdijk in the Netherlands. Due to Corona, this unfortunately was not feasible. Hopefully, this webinar event will give you a good impression of all the work that is performed in the REvivED project concerning multi-stage electrodialysis seawater desalination. The organizers did their very best to achieve this for you. And with pleasure, I take the opportunity to thank all of them for the work and energy to make this webinar to a success. That concludes my short introduction. And with pleasure, I give the floor to our CTO Simon Grasman, who will lead you through the presentations. Enjoy the webinar. Simon, will you take over?
Okay. Hello, welcome everybody to this webinar of the REvivED project. On behalf of REdStack and all the project partners of the REvivED project, my name is Simon Grasman. I'm the CTO of REdStack and I will be your host during this webinar. This webinar was supposed to be hosted live on the 1st of July, but unfortunately, due to a technical issue related to the security settings of our network from the ICT provider, most of the attendees couldn't log in and therefore weren't able to attend. As an alternative, we made this recording, ensuring in this way that everybody who is interested in the results of the REvivED project is able to take notice of them, and in this way informing them about the progress being made. The program of the webinar was first the opening by Rick Siebers, which just has been shown, followed by a presentation by Michael Papapetrou. He is the project coordinator of the REvivED project. He will inform you about the project in general. Then we go on to the content of this webinar in the sense of the multi-stage electrodialysis system to desalinate seawater, which has been tested on the Afsluitdijk. This will be done first by an introduction movie showing you the pilot that has been realized in its environment on the Afsluitdijk, followed by two presentations. The first by Gijs Doornboes, he is a PhD researcher at Wetsers, and second by Jordi Moreno, process technologist at REdStack. Since this webinar is recorded, the Q&A chat can't be used. As an alternative, we offer you the possibility to send your questions depending related to the presentations or any other questions related to the project. You can send them by email to request@redstack.nl. This email address will also be mentioned in the email accompanying this, the sending of this video. Please indicate in the email with the question to whom the question is directed, and then we will make sure that the question is being answered. Now I would like to give the presenter mode to Michael Papapetrou for his contribution to this webinar.
Thank you very much for the introduction. My name is Michael Papapetrou and I'm going to present to you the project REvivED Water. So the full title of the project is Low Energy Solutions for Drinking Water Production by a Revival of Electrodialysis Systems. As the first slide, I have here to you an overview. This is quite an old picture. It is outdated at this stage, the percentages, but it still gives a nice overview of desalination technologies. So if we start from the bottom right, you see the multi-effect distillation, and on the top right, the multi-stage flask. These are the thermal desalination technologies. According to this graph, they have more than half of the market share. At this stage, they have definitely less than half of the market stage, but still they're a big part of the salination systems. The main element here is evaporation of water. This is how the salts are separated from the water. The water evaporates and the salts remain behind. We use thermal energy. These are the thermal desalination technologies. They have been optimized over many decades, and they have reduced their energy consumption as much as possible. Energy consumption is still significant. There are physical limits on how low we can go. And this is why reverse osmosis has taken over. Reverse osmosis started a few decades ago. Electricity is the driving force that pushes the water through osmotic membranes and leaves the salt behind. Now, this has been also very, very much optimized. The prevalence of the technology has been based on the osmotic membranes. They have become much, much better and much cheaper over the years. And now this is the main state-of-the-art technology that is used in the majority of plants around the world. The move from thermal to electric energy and going through membranes has been a revolution. On the bottom left, though, we see electrodialysis. This is still a niche technology. Membranes are used and electricity, but the main difference is that it's not water flowing through membranes, it's the salt that goes through the membranes. In principle, this can be more efficient because there is not large volumes of water having to go through membranes that can create problems in the membranes and require a lot of energy to push them through. So this can be, in principle, a more efficient technology, but it has not yet taken an important share of the market. So this is where our project focuses, on the technology and on the ion exchange membranes that will have the performance and the cost that will make them competitive. So the aim of the project is to develop and test innovative electrodialysis systems that showcase their benefits in mainstream desalination applications. It's a Horizon 2020 project. It has about 10 million euro budget. It started in May 2016 and it was supposed to finish this May, but it has been extended by 3 months until July 2020 because of the coronavirus restrictions that stopped the work in the last few months. There are 10 partners from 6 countries. And you can see here the logos of the partners. As I said, the project is coordinated by Fujifilm. REvivED, the company hosting the webinar today, is a partner building the stacks and the system in the Netherlands. We have Troons from Switzerland that built the system in Spain, and Fesan that does together with Deocum and Fujifilm the systems for brackish water in the developing world. And we have research institutions that work in the modeling and in the design optimization of the systems, and AquaTT for the dissemination communication. There are 3 main phases in the project. In the first phase, for the first 2 years, we've been, for the first 1 year, we've been working on the background, on knowledge and components development, prototypes for testing, design and specification of pilots. After that, we went to the phase of scaling up the main components to reach industrial scale and to start the construction of the pilot plants. And for the last year and a half, the pilot plants have been under construction and operation, and we focus on exploitation activities and market introduction plans. So here I have just a few pictures. So on the top left, you see a picture from Somaliland, I believe, and this represents the 8 pilot plants that we've been building, and 7 of them are operating in developing countries. The first one in Somaliland started already back in 2017, and this has been going very well. So they're quite efficient, the plants, and they're low cost, and they're operating well. We are learning a lot by operating in very remote locations. We do remote monitoring, and there are other videos and material on the website covering these plans. Then on the top right, we see the system in Spain. The system in Spain combines electrodialysis with reverse osmosis. So we take seawater, it's a 25 cubic meter per day system. We take seawater in Spain, The plant is hosted by FAXA, and we use electrodialysis first, and we desalinate about 50%. And for the rest of it, we use reverse osmosis. This is an interesting application given the prevalence of reverse osmosis in the market, to show how electrodialysis and reverse osmosis can work well together. And on the bottom, you see the plant for which you will hear much more in today's webinar. It is the multi-stage electrodialysis system for seawater desalination in the Netherlands. And I just would like to thank the European Commission for the funding and all the partners for the fantastic work. It's been a long journey, 4 years. A lot have been achieved. A lot of new opportunities have opened, and we're looking forward to the next stage after the completion of the REvivED project. That's all from me. You can always find more information on the website of the project, and thank you very much for your attention. Back to you, Simon.
Thank you, Michael, for your contribution to the webinar. Now, after this general introduction, we will move to the part of the webinar focusing on the desalination of seawater using multi-stage electrodialysis. The final result of this work is the pilot as it is constructed and operated at the test facility of REvivED on the Afsluitdijk, operating on real seawater, desalinating it to drinking water. The work started with the development in Wetses, supported by the industrial partners Fujifilm and REvivED and the modeling work of the University of Palermo. As a next step, a pre-pilot has been constructed on the Afsluitdijk to test in real life, as a step towards a real pilot as it is constructed on the Afsluitdijk. To introduce you to the pilot, since we can't show it in real life, a movie has specially been produced to show you the pilot at the Afsluitdijk test facility.
A growing global population compounded by effects from climate change means the world is in critical need of clean and safe drinking water. Seawater desalination has been widely adopted to address this need. However, current methods are highly energy intensive. A sustainable future requires an energy-efficient solution. REvivED Water is an industry-driven project funded by the European Union. It brings together 10 European partners aiming to solve this challenge. Electrodialysis uses electric current to push salt ions through specially designed membranes, leaving behind drinking water. This method is energy efficient and produces less waste products than conventional processes. At REdStack's Blue Energy Test Facility, located at the iconic Afsluitdijk in the Netherlands, researchers have been testing a new multi-stage electrodialysis system. This pilot has successfully demonstrated full-scale desalination of seawater. The development of this energy-efficient desalination was accelerated through the knowledge and experience gained by REdStack's industrial and academic partners over the course of the REvivED Water project.
We worked on this project for like 4 years, and when we the first 3 years we worked with artificial seawater. That was already nice when we met the target, but later on we worked with real seawater, and that was actually quite challenging, and that really felt really good that we were able to desalinate the real stuff actually to drinking water concentrations. That was a really a big achievement.
Based on the results achieved in the REvivED project, a 3-step desalination process was chosen for the pilot, with a capacity of 25 meters cubed per day. Each step has been specifically designed to optimize energy efficiency and maximize desalinated water output.
Behind me, you can see the pilot of REvivED, where we have a multi-stage electrodialysis desalination technology, and the great achievement is that we can do the same job with more energy efficient. Being energy efficient is better because we consume less energy, so the cost of water will be less.
We made it happen. We did a long, extensive test of like 3 weeks, where we desalinated from seawater to almost drinking water. So we're quite happy that we achieved the target, and we also met the energy consumption demands.
By the knowledge of REdStack on developing and upscaling the blue energy technology, we could accelerate the technology in a sense that is ready for commercialization.
It's quite challenging, like the world is on my shoulders.
Feels good? Feels good.
This pilot at the Afsluitdijk, along with other pilots and results of the REvivED project, has brought electrodialysis one step closer towards commercialization and an energy-efficient future for desalination.
I trust this video was a nice introduction to the concept of multi-stage electrodialysis and the pilot as it is realized in special. Next, I would like to give the presentation mode to Gijs Doornbos. Gijs has been working as a PhD researcher for the past 4 years within the REvivED project, looking for the most optimal configuration to desalinate the water with the minimum energy consumption possible. Currently, he is employed at REvivED to continue his interesting work on electrodialysis. Gijs, the floor is yours.
Thank you, Simon, for the introduction. My name is Gijs Doornbos, and in the REvivED project I was working as a PhD researcher at WETSES and at the Eindhoven University of Technology. And currently I'm finishing my PhD thesis and I'm continuing the research on electrodialysis in REvivED. And I would like to guide you through the advances we made in electrodialysis the last 4 years. So the title of my presentation is Electrodialysis for Seawater Desalination from Lab Scale to Pilot Scale. First, I would like to give you a brief explanation on how electrodialysis works. So you can see in this schematic that the ions move through the ion exchange membranes, and on the left side you see the positive electrode, on the right side you see the negative electrode. Between the electrodes there are the ion exchange membranes piled. So we have anion exchange membranes and cation exchange membranes. And under the influence of an electrical potential difference, the ions, positively or negatively, are transported or migrated through the ion exchange membranes. We see, for example, that the chloride moves to the positive electrode and sodium moves to the negative electrode. And then there is a dilute and a concentrate stream produced. In the next 3 slides, I would like to give you a short overview of the different research topics that we covered. And later during the presentation, I will address for each topic the most relevant results and the most important conclusions. So first, we investigated a conventional single stage and we compared it to the desalination performance of a multistage. And on the right side of the slide you can see that we tested a segmented electrode. So it's the same as a single stage, but the electrodes are separated in 4 different electrodes, and we compared it again to the multistage system. After this we saw that the multistage is probably the way to go. We looked into the membrane, the different amount of membranes in the multistage in each different step of the desalination process, and we also investigated the variation of membranes with different properties in different stages of the desalination process. These 2 research lines we combined, and to the right side where you can see that we tested both the membrane redistribution but also the influence of the different membranes with different properties. So we went from the lab using sodium chloride to natural feed water. First, in the top picture you can see that we tested 4 stacks. These 4 stacks were equipped with different membranes with different properties. And then we put these, the knowledge we gathered, we built up a multistage and so after the tests in the WETSES laboratory, using simple sodium chloride solutions. We moved forward to more complex solution using multivalent ions and mimicking seawater, followed by feeding the system with natural feedwater. In the top picture you can see that you see the experimental setup where we compared membranes with different properties to be installed in the first stage of the multistage. As a multistage allows to remove the multivalent ions before in the desalination process, but multivalent ions also increase the resistance in subsequent stacks. So first we analyzed in what of the 4 stages should have a multistage, what membranes to be installed in the multistage, which you can see in the bottom. So to start the comparison between the single stage and the multistage, you can see here in the left you can see the single stage, on the right side you can see the multistage. And if we can look into the results, we see in the left figure the limiting current density per electrode pair. And you can see that for the multistage we tested different feed flow velocities, while for the single stage we tested only one feed flow velocity of 10 millimeters per second. You see that the single stage measures only one limiting current density because it's one big electrode, and for the multistage we have per electrode pair a different limiting current density. Limiting current density is basically the maximum driving force that you can apply in order to reach an energy efficient desalination process. So you can see then the corresponding outlet concentrations in the right slide, in the right of the right graph, where you can see that the multistage in the electrode pair 4 goes to really low concentrations, while the single stage only remains at around 100 millimoles. So that's relatively high, and it's not yet drinking water concentrations. Drinking water concentrations are around 8.5 millimoles, which we almost reach in the multistage, but not in the single stage. So from this we can conclude that for desalination to drinking water, a multistage is required. Then we went and compared the multistage to the segmented electrode stack. And if we then look into the similar figures, but then for the segmented and the multistage, you can see that the segmented stage in each electrode pair allows for a lower limiting current density. And as a consequence, in the right figure, you can see that the segmented ends up with a higher outlet concentration compared to the multistage. So also from this research, we can conclude that the multistage is required for the desalination of drinking water. Then we investigated the multistage further because we almost reached the concentration and we had a specific energy consumption, but this could be more improved, and that we did by studying the effect of membrane area in each stage. So we distributed the membranes in different ways over the multistage, and we also tested different membranes with different properties in different steps of the desalination process. So as you can see in this slide, you can see on the left side a schematic of a method that we used where the cell pairs are distributed differently over the stages. And in the right side you see the corresponding feed flow velocities over the different stages. So basically we want to lower the residence time or the feed flow velocity in the first stage, as you can see in the right graph, and we want an increased feed flow velocity in later stages. If we then summarize all this data, we see that for the single stage the dilute concentration was still relatively high at 120 millimoles, while drinking water is 8.5 millimoles. The segmented electrode is improving in desalination performance. We reach a lower dilute concentration. But for both configurations, we don't reach it, so we didn't measure the energy consumption. And then for the multistage, for the non-optimized multistage, we saw that we reach 11 millimoles at an energy consumption of 3.6 kilowatt-hour per cubic meter. In the schematic you see below, which we call the optimized multistage, we improved this dilute concentration to 5.4 millimoles, and the energy consumption is 2.2 kilowatt-hour per cubic meter. So this scheme shows both the different membrane distribution and the implementation of membranes with different properties. So we do the bulk desalination, most of the desalination with type 10 membranes from Fujifilm, and the more black circled boxes, we see that was type 2 from Fujifilm we used. And using such a scheme, we were reaching such a low diluent concentration and energy consumption, we were ready to test, to continue the tests with a more complex system than just sodium chloride. So we tested these 4 stacks with different membranes to be installed as a first stage of a multi-stage system. So we went from sodium chloride to artificial seawater to natural feed water or natural seawater. If we then see these results, we tested 2 different membranes. We tested a type 10 cation exchange membrane and a type T1 cation exchange membrane, both from Fujifilm, and as an anion exchange membrane we used a type 10 too, to build up an electrodialysis stack. The cation removal in a diluate for calcium, you can see that's more or less the same between both types of membrane, but for magnesium there is a higher removal using type T1, so that if we can remove more magnesium already in the first stage of a multi-stage system, the resistance is less likely to increase in subsequent stages of a multi-stage system. For sodium we see a similar cation removal, so that is already that's good. If we then go into the middle plot, you can see that the conductivity over the different current densities is the same for the type 10 and the type T1 membranes. The diluate goes linearly down and the concentrate goes as a consequence linearly up, so that's a nice result. And the voltage per electrode, the voltage per cell pair for type 10 membranes is 20% higher compared to the type T1 membranes. This is good. This is a good result, because then this would mean that we would remove more magnesium with type T1, but we also have a 20% lower voltage, and this voltage translates directly to a lower energy consumption, because we see that already in the right plot we can calculate that we have with type 10 a 20% lower power, and then if we see that the amount of water, the amount of water we yield with type 10 and type T1 is the same, so that means that we can say that with type T1 we have a 20% lower energy consumption compared with type 10. So then we took this knowledge to the Afsluitdijk, where we built up in the research facility of REdStack a multi-stage system with 3 stacks. In stage 1 we placed 100 cell pairs, in stage 2 50 cell pairs, and in stage 3 25 cell pairs. The membranes we used in the first stage were the type T1 with the more magnesium removal and lower energy consumption. In stage 2 we used normal type 10 membranes to do the main or the bulk desalination, as we call it. And in stage 3 we installed a Fujifilm type 2, which we used before, that these membranes were beneficial for lower water transport, and that also gives us a lower energy consumption because we yield more water in the end. If we then go and look to the results of this multi-stage configuration, we see that the TDS over the 14 days that we tested is slightly varying. As a consequence, stage 1 is also varying in outlet concentration. We see that this effect is less pronounced in stage 2, and that stage 3 has a more horizontal behavior. So that means that whatever happens in stage 1 and 2, stage 3 is capable of giving a constant outlet concentration, which tells us that the system is robust. Ideally, we would see for all stages such a horizontal line, but in this research in this multistage, which we built on the research table, we were not able to implement, for example, a pH control and such measures. So this kind of problems we tackled already in the bigger multistage, in the bigger pilot, which Jordi will tell you later on about. But nevertheless, we reached an energy consumption over the 14 days of around 2 to 3 kilowatt-hour per cubic meter, which is already a good result. So then, to summarize the results, we compared a single stage and a multistage, and a multistage system is required to desalinate to drinking water conditions, where in a non-optimized system we saw that the energy consumption was 3.6 kilowatt-hour per cubic meter. We compared a segmented electrode stack and a multistage, and then we also saw that the multistage still is required to reach the drinking water. If we then optimize or look further into the multistage, we see that the membrane area distribution within the multistage and the variation of membrane properties show that drinking water can be produced at an energy consumption of 2.2 kilowatt-hour per cubic meter. And for natural seawater desalination, we needed to install the multivalent permeable cation exchange membranes. And we desalinated the natural seawater of 22.9 gram per liter to 1.9 gram per liter using an energy consumption of roughly 3 kilowatt-hour per cubic meter. The next step is this pilot system, which Jordi will explain you later. And we hope to be able to do tests over a longer period of time. And then I want to acknowledge the REvivED project and its partners, but also the different students I've worked with over the years. And I would like to thank you for your attention.
Gijs, thank you for your interesting contribution. Now, from the work done by Gijs, in cooperation of course with the project partners, we will move to the pilot that has been realized on the Afsluitdijk as a result of all this work. The design of this pilot and the results of this pilot will be presented by Jordi Moreno. Jordi has been involved with the project for the past 3 years. Jordi, the presentation mode is yours.
Thank you, Simon, for your introduction. And now I would like to present my presentation, and it's the title is Scale-Up Multi-Stage Electrodialysis for Seawater Desalination. I'm going to present some pilot results, and I have to say that this work has been done with a bunch of colleagues like Christian, Simon, yourself, Jorin, and Auka, that they were our stack builders. And the breakdown of my presentation is going to be this one. So I'm going to present a little bit of a modeling input that we use for design and development of the University of Palermo. Also with the results of Gijs, this actually create the basis of the design of the pilot. Later on I will present the pilot because I think it's why we are all here, to see what we design and what has been more or less what are the characteristics of the pilot and why we choose for that characteristics. That is also important. As well, I will present a selection of the results that we obtained during the last month, a few conclusions and a little bit of outlook. So first of all, thanks to my colleagues in the University of Palermo, we received some modeling support in order to design and to develop the multi-stage ED electrodialysis. And the group from Giorgio Micale and Andrea Cipollina, they and all the students they have, during these years we have been working really closely and also supporting the data we got also from the laboratory from Gijs. So in that sense, our colleagues from Italy throughout the project, they develop this hierarchical model where they start with the cell pair modeling, and actually this includes the transport phenomena and the electrical circuit. They scale up into stack parameters. So in that sense, they could include more variables like flow and a little bit of hydrodynamics and also performance and like ionic shortcut currents. And with all this knowledge, we could really model a plant or simulate how it's going to be the future plant and what was the most interesting configuration for our plant. They had a lot of a lot of publications during these years, and I think actually that was really interesting and really helpful. So with the model they developed at pilot level, we tried several things. The first one was to model what was the best membrane distribution in order to get the better energy consumption. So we assume some conditions like using the spacers we use already on the pilot, inlet salinity at defined temperature, and we target 25 cubics per day of product. So what they did is like they make two scenarios. One scenario where all the stages are 150 cell pairs, and another scenario where the membrane distribution is a little bit different. So they put more membrane at the beginning than at the end. So a little bit like Heis explained it, that we see that we can speed up the flows. And actually, if you see at the specific consumption, is way favorable to distribute the membranes along the path and also speed up a little bit the flow, because then it overcomes one of the limitations of electrodialysis. That was really promising, and actually we choose a three-stage configuration with a membrane distribution, but also we wanted to look at really a little bit more what will be the membrane properties, on if we can, on the membrane properties when we make the plant, and what will be the impact of those. Also in this case, they also were able to model the cross-flow configuration. The previous one was a conventional stack actually, so a co-flow configuration, and now it's already cross-flow, that is like our stacks. They decrease a little bit the temperature, and also they adjust the influent salinity and also the production. So also here we can see that when they simulated the plant, they get more or less a specific consumption of energy consumption of 1.7 kilowatts. And then we will see that later that we are not far away from this number. So actually the modeling was really helpful. And actually this was a validated model because they used the data from Heis in the laboratory, and also from Maria Georgia and from Antonino from the laboratory. So it was really helpful to design the stack. So thank you very much to the colleagues of the University of Palermo, because they were really helpful in this stage of the project. So actually now I go a little bit into the pilot, and I already say that it's a three-stage electrodialysis system where we use an asymmetrical membrane distribution, but also we use different membrane properties of the membrane. So in that sense, I mean that the first stack is bigger than the last stack. So actually what it does is that the water flows every time increase in velocity, but also thanks to Fujifilm, we use two different membranes, type 10 and type 12 actually. And actually this type 12, actually what it does is that we put it at the end, and it allows to control the water transport. So actually we can avoid some losses when the gradient is super high. Well, super high, no, when the gradient is higher. We also design a stack, a pilot that has multiple operational configurations. So it allow us to test different configurations, and I will explain them later, because also you will see what is the impact of each configuration. We did this together with Pure Water Group, and it's and they had quite a lot of knowledge, and they helped us to develop this pilot, and it was really interesting, the conversations we get with them. Also, we could integrate the new stack design. Actually, you can see it here. It's a tube stack, and normally we work in a little bit more pilot, or not pilot, a more prototype kind of stacks, and now this is what is really close to a product. So actually we also develop our engineering skills on the way through this project. As well, since we are using natural feed waters, we needed to include also a prefiltration skid, and actually we learn from our pilot at Afsluitdijk, because we had a lot of experience there, but also at the pilot we have in Burriana, in another work package of this project, that we see which problems they had and also how they solve it, and we get the best lessons from that experience, and we implement it also to this pilot. So it was really beneficial, this transference of knowledge between partners, because it helped us a lot to define what was the minimum design for, or requirements for our pilot. So here it is. This is the pilot within the Afsluitdijk installation, and in that sense we choose for two stages with two skids with 3 stages, sorry. So actually this is what I call a skid, this is also another skid, and here you can see the 3 stacks. But if we look closer, this is the pre-treatment. So the pre-treatment was the waters at Afsluitdijk are natural feed waters, and we use rapid sand filtration. So it's a dual media of anthracite and sand layer. After that, we include a 30 micron cartridge down to 1 micron cartridge, and later on active carbon to remove some more organic compounds of the water, like humic acids. Here we have the first stack. I call it stack 82. This was the design number, but this stack for us is stage number 1. It's equipped with Fujifilm type 10 membranes. We have 192 active area of membranes with 496 cell pairs, and the spacers from DOCOM are 260 micron thickness. The configuration, as I said, is cross-flow. So now we go to the second stage, and in the second stage we can see that we already have half of the cell pairs, so that actually will mean that the water will flow twice faster later on, also with the same type of membrane, Fujifilm type 10, and the same spacer configuration. And the last stage is a little bit different because we use Fujifilm type 2, and this is a special membrane that has special properties, and actually we place it in this position because we expect that here will be the highest gradient, so the more concentrated versus the more diluted, and we want to avoid losses in water transport. And this stack has 45 square meters of active area of membrane, and also the same configuration. So as you can see, the 3 stages, the water is speeding up. This is the flow process diagram. It's a little bit more, a little bit complex because, well, it's not really complex. This is a straightforward design, but you can see that we have a lot of sensors, and actually that helps us because otherwise it could not be fully automated. And what we have is flow meters, pH meters, temperature, pressure, and conductivity sensors. Also, we have DC power supplies with EDR capability. This is something that HICE could not do it, but we had in this pilot we could do it also, again thanks to Pure Water Group, because they help us a lot designing this and they share a lot of knowledge also. And it's fully automated, so actually it could work 24 hours, 7 days a week. So now I'm going to explain a little bit a selection of the results we got during the operation of this pilot. First of all, I will present 2 series of experiments with artificial seawater, and later on 2 series of experiments with natural feed waters, but also longer time. And the first one I want to explain is this, when we're using artificial seawater, and artificial seawater is nothing else than sodium chloride in a closed loop. So we recirculated the water during the experiment just to characterize what was the LCD points for each stage and also what was the energy consumption at that point. So it's a little bit more controlled situation, not really jumping into the difficult natural seawater. For a straightforward, what we call is that is when we feed the waters and they go through the 3 stages, and 50% of the product is 50% of the feed water are product and 50% of the feed water is concentrate. So actually this is the easiest way of operating a multi-stage pilot. But it has good things and bad things, and one of the good things is that you can you have a higher recovery, but in the other side is also, if you want to desalinate faster to avoid the concentration gradient, you need to really speed up the flows, and at some point that is not possible. And but here at the beginning what we have is like we test 3 different flows, And the first one is like 1,000 liters per hour, so that results in 24 cubics per day. The second one, we speed it up and is 1.5 cubics per hour, so that is about 36 cubics per day. And the other one is already 2 cubics per hour, so it's about 48 cubics per day. And what we can see here is that the absolute rejection, so in the first stage, on the blue ones, we see the first stage for each velocity. We see that it does most of the job, so actually it cuts by almost half the concentration. That means that if you start at 22.8 grams, you already end up at 11 grams, more or less, a little bit more because it's about 60. The second stage removed 24%, and the last stage 12%. You can see that as soon as you speed up a little bit the velocity, also the last stage is able to remove less and less and less, but there is a little bit of redistribution between the stacks. If you look at the energy consumption, of course, as soon as you increase the velocity, it also increases the energy consumption. And this is really clear when we use a really high flow rate. So you can see that the first stage is about taking 1.6 kilowatts per cubic meter of product. The second stage 1.14, and the last stage is 0.40. So actually, most of the job, as we say, is done on the first stage, and it's also that one that consumes more. Unfortunately, this was not enough to reach the target concentration. Our target concentration was 0.5 grams per liter, that is the same of 10 millimolar. So actually here you can see a graph that we have the energy consumption and the apparent flux. The apparent flux is the liters you produce of product per square meter of membrane per hour. So actually that gives us an indication of how well are we using the membranes, because the membranes is one of the key components of these stacks that is the most expensive, so also at the same time is limiting. And if you control the apparent flux, you can already control a little bit more what will be the capex necessary in order to achieve the result. So at this moment we can see that at low flow rate, so in this case 24 cubics per day, we see that we could reach 20 millimolar, so it was a little bit above target. When we increased the velocity, we were able to go down. But at the same time, when we increased a little bit more, it was not enough, and actually our consumption was really, really high. So we decided that the straightforward probably was not the best. So we make one step back, and actually what we changed is we changed the configuration, and we went to diluate split. And diluate split is nothing else than the concentrate at the straightforward. But what we do is at the end of the first stage, we use the product, and then we split it into the second stage and the third stage. So actually, this has a benefit, because then we avoid the losses in water transport in the second stage and the third stage, because this gradient is less than the gradient we got before. But as you can see already, product is only 25% of the feed. And actually what it does is that your LMH goes down. So we need more membrane to do the same job. Well, there's a little bit of background, but if we look at the data, we see that now instead of using 1,000, 1,500 and 2,000, now we need to use a little bit lower velocities, because this is also the first stage. We need to split the dilute, so there is no enough water available in the stack. So the first velocity is 500 liters per hour. That is also about 12 cubics per day. The second one is 750 liters per hour. It's about 18 cubics per day, and 1,000 is about 24. So actually the target of our pilot. So here we have the rejection again against the velocity, but for the different stages. And you can see also that the first one is doing most of the job. Actually, it's the same performance of the previous configuration. But the second stage is doing about a bit more, and the last stage is also to do a little bit more. Actually, these results, since we don't have water transport, then the first stage is the one taking most of the energy, but the second stage and the third stage are not consuming that much. And that is really interesting because it allows us to more or less reach the target we want, of course at lower LMH because we are splitting the water and we have less water recovery, but we almost reach the target we wanted. So this is in the right direction. And after this we did, well, here you can see that what I say, the first stage has a higher energy consumption. Of course, we have less water transport, but we have at the expenses of low water recovery. But then we decided to make another twist on the configuration because we could try different operational modes. And what we did now is we did the concentrate recycle. So actually, in order to increase the water recovery from 25 to 37, what we did is we increase the concentrate, we recirculate this concentrate that we were discarding. So actually we are creating a higher gradient on the first stage, but that allows us to gain more water recovery. For this experiment, since we are concentrating a little bit on the first stage, we decided already to do it with natural feed waters. And actually I have to say that at that moment the Afsluitdijk, this data is from, if I'm not mistaken, from February. So that means that it's about 16-18 grams per liter in the inlet and temperatures about 6 and 8 degrees on the inlet. Here we can already see that the graphs are changing. So on the first stage we see that we can do a little bit less than before, and but in the second stage is picking up, so it does more desalination, and the last stage is similar to the other experiments. And this is also due to that the first DC power was a little bit limited in voltage. The water was so cold that the resistance of the water was really high, and we could not really desalinate everything that we wanted on the first stage. So that's also why it came to the second stage. If you can see that the energy consumption, the same, as soon as we speed up the waters, we also increase the energy consumption. But especially on this one, it's quite low already. We are a little bit below 2 kilowatts, and we are really close. Well, actually we hit the target. As you can see here, we have 10 millimolar at below 2 kilowatts. And then later on also at 18 cubics per day, we could reach the target concentration. But when we speed up the waters, due to the lack of voltage on the first stage and we could not desalinate enough, we have only 32% desalination, and this used to be 60% desalination. We could not really reach the target. Well, but as you can see, we can keep the same LMH, so the apparent flux, we can keep it and we can decrease a little bit the energy consumption, but we are really hitting the target that we want. So remember that here the temperatures are low, but also the DC power supplies, they were limiting a little bit at high rates. This was really interesting. So we decided to make another twist, because still we were a little bit low in water recovery, so we tried to increase the water recovery, and what we did is we used the concentrate, the final concentrate, we feed it back to the inlet. And that was really interesting, and this one we already make it for a little bit longer. So we target about 12 cubics per day, so this is more or less 500 liters per hour, with the same concentrations as before, but with this loop. So now we get about 66% water recovery. This is a little bit better than the straightforward configuration. And here you can already see a long-term experiment, because we thought this is the best way to see the performance. Also you can see that we have a little bit of jumps when we do the EDR. And here what we have in this graph is the TDS versus time, so actually time versus TDS. And in blue we have the seawater concentration, the inlet, then the product stage is the product at the end of stage 1. In gray we have the product after stage 2, and the yellow is the product after stage 3. I already put a target line, so actually you can see this line that we are most of the times below. That means that that line is 0.5 grams per liter, so it's the same of 10 millimolar. As well, here we have the energy consumption per stage, so you can see that the first stage is the one that is taking most of the energy. The second one a bit less, and the last one almost is the one that is the lower of the three. So the average is around 2, and actually indeed the average is 1.94 kilowatts per cubic meter. And the outlet concentration, it has an average of 0.5. We also have high peaks and low peaks, and that is due to the EDR times. So when we switch the waters and also actually we switch the polarity and we switch the waters, then sometimes there is high peaks on concentration, but they are only last a few seconds, so there is no representative in time. So this was really promising, so we wanted to speed up a little bit more. And speed up, it means to create more product. So what we did is like from 500 liters per hour, we increased to 750 liters per hour. So actually this equals at around 18 cubics per day, the same water recovery. So we keep the same concentration, and we decided even to make it a little bit longer. So in this experiment, we were looking at data for about 7 hours. And as well, we also have the seawater desalination. We can see that it goes down. This is due to the concentrate loop. Also because it's changing during the day, the concentration, because we have the tides in the North Sea. We have the outlet of stage 1, so you can see that the biggest drop of salinity, so the job is done on the first stage. That also explains why it's the one that is consuming more energy. Then here we have the outlet of stage 2, that is almost below 2 grams, and then the outlet of stage 3, that is almost polishing, is just below 0.5. So actually for several hours we could really reach the target concentration without consuming too much energy. The mean energy, so the average energy for this experiment was 2.5 kilowatts per hour per cubic meter product, with an average product total dissolved TDS of 0.37. So really good results. And here now, to close up, I will draw some conclusions of the experiments and also the whole project a little bit on this work package. And what I can say is that the lab work done by Hayes and other PhD students from University of Palermo and also University of Ghent, and the validated model that they developed was really useful to design the pilot and also to size the stacks. That was really important, because then we needed to test. We don't need to buy 3 or to build 3 pilots. With only one, we could already go really into the most optimal configuration, thanks to the modeling work. Also, we could test several operational modes at different flow rates, and that actually gives us a lot of insight on what is the best configuration if we wanted to, in the future, to build up a full-scale facility, because it depends on the water quality, but also looking at different properties of the membranes or distribution of the membranes, and also the operational modes. It gives us a little bit more freedom to design the best flow diagram for each application. Later on, we saw that by process optimization, the water recovery could be double while maintaining the apparent flux and water quality. So actually that means that with a little bit of creativity and reusing the flows, we could keep the LMH pretty good. And actually that what it does is that we can increase the water quality without needing more energy, more membrane area. So that was also really good. We also have, well, here some results that I summarized it here in the conclusions. Is like we reach target concentration, that is 0.5 grams per liter, using natural feed waters. And by producing 12 cubics a day, we could produce this product at almost 2 kilowatts per cubic meter of product. And when we increase a little bit more the product production to 18 cubics per day, we reach 2.5 kilowatts per hour per cubic meter. Of course, we still have some time in the project to do things, and what we wanted to test is like we are going to add a 4-stack in the system. We saw from the experiment of Hayes that maybe 4 stages was the optimal, and because he saw that he had really good results. So we also want to test that on the big pilot. So we add a new stack, but without adding new membranes. So what we are going to do is we are going to take some membrane from the first stage and we are going to place it at the end. So we are going to redistribute the membranes, and in order to get better results and a bit more stable at higher recovery. So maybe now with a 4-stack, the straightforward configuration will be enough to get the target concentration, and in that sense maybe we can also increase the water production. And of course we want to test at different temperatures and different seawater salinities, and that is quite relevant because what we saw is that we were testing at low salinities, like north water salinities, but the temperatures were also really low. And the temperature has a high impact on the energy consumption. So now what we want to do is that we saw that the electrodialysis is interesting in the Middle East countries, and they have higher temperatures, but also higher salinities. So we want to study more what is able to do our pilot on those concentrations and temperatures, because then actually it will help us a lot for the business case and also to find applications in the future for this technology. And with this, I would like to conclude and say thank you. And if you have any question, please just send it to my email that is here in the screen. And well, thank you very much for your time. And I say that, well, I give the connection back to Simon. And thank you very much, everyone, for listening to my presentation.
With Joris' presentation, we come to the end of this webinar. Normally here, the Q&A session would have followed, with the panel members, the 3 presenters, and Jan Post. He's a program director at Wetsers, and Luigi Guerrieri, postdoc at the University of Palermo. If you have any questions related to the content of this recorded webinar, you can send it to request@redstack.nl, as mentioned before, and we will make sure your question will be answered. I hope you found this an interesting event. And then before ending this webinar, I would like to thank all the project partners for the contribution in the REvivED project. It's a pity we can't make a toast together to end this project and to look forward to new opportunities in the near future. A special word of thanks, of course, to the European Commission for financially supporting this project. And with this, I would like to end this webinar. Again, thank you for your attention and have a nice day.